The biggest mistake leaders make about artificial intelligence is thinking the constraint is the model. In practice, the constraint is permission, measurement, and accountability. Many organizations already have capable systems on hand. Far fewer can safely delegate real work to them. Start with a reframing that changes everything. Once an AI can call tools, move data, and trigger workflows, chatbot stops being a useful category. You are no longer buying a conversational feature. You are deploying a control plane that can act inside your institution. That means identity, access control, logging, approvals, rollback, and incident response become the product. The interesting part is not the prompt. The interesting part is delegated authority. So a practical question becomes, how much authority is the system allowed to hold? Some systems should only advise and never touch production tools. Others can call tools, but only in a sandbox. Higher up the ladder, you get agents that request approval for each consequential step. Finally, you get bounded autonomy, where actions are permitted inside a defined envelope. The frontier in the near term is not reckless autonomy. It is disciplined delegation, with fast revocation when things go wrong. From there, the economics shift in a way that catches even senior teams off guard. Cost per token is a seductive metric, because it is simple. Yet it is often the wrong unit for strategy. What matters is dollars per validated outcome. That includes retries, human review, remediation, and the cost of errors. It also includes time, because tail latency can break a workflow even when averages look fine. An inference factory is not a metaphor. It is an industrial serving system with routing, batching, caching, monitoring, failure isolation, and capacity reservation. That industrial framing forces a second metric into the boardroom: joules per validated task. As reasoning scales, energy accounting stops being a facilities detail, binding constraint on what you can automate and how fast. Cooling, heat density, and memory movement start to dominate the real cost curve. Data has to travel through networks, across racks, in and out of memory, and those movements are often the hidden bill. When people say compute is the new oil, the more accurate claim is that compute is the new grid planning problem. Orchestration is part of that constraint too. When workloads span cloud and edge, scheduling stops being an administrative afterthought. It becomes a technical frontier, because placement decisions affect latency, cost, reliability, and power. A system that is cheap but late can be worse than a system that is expensive but on time. For capital allocators, this means you do not just buy models. You buy serving discipline, measurement, and operations. Interoperability then becomes the next ceiling, and it is not mainly technical. It is institutional. Once agents work across vendors, departments, and jurisdictions, you need machine-readable permissions, signed instructions, provenance, audit trails, and revocation channels. Think about what happens when an agent in one organization triggers work in another. Who is allowed to request the action? Who can verify the request? Who can later reconstruct what happened? Without shared trust infrastructure, you get isolated automation islands that cannot safely connect. Now layer on the interface shift, because it changes the risk envelope dramatically. Typed prompts are episodic. Ambient and multimodal systems are persistent. Microphones and cameras are not just inputs. They are always on sensors that can capture context before a user forms explicit intent. Voice also blurs command and conversation. A casual sentence can sound like an instruction. Meanwhile, multimodal records create privacy and provenance burdens, because the system can store not only what was said, but what was seen and what was inferred. That is why interface design becomes governance. Consent cannot be a hidden clause in a policy document. Logging policy cannot be improvised after deployment. Attention is a scarce resource, and systems that shape attention can shape decisions. When you put AI into rooms, vehicles, factories, classrooms, or hospitals, you are not just adding convenience. You are installing a new layer of observation and influence. A different kind of frontier appears when AI enters research and science. The most important shift is how you judge success. Benchmark scores are weak proxies for discovery. What matters is validated experiments, replication rate, and cycle time reduction. A credible discovery system ties outputs to auditable code, measured data, uncertainty reporting, and laboratory constraints. Closed-loop science depends as much on lab automation and data standards as on model capability. In other words, the bottleneck is often the physical and procedural interface between a model and reality. Decision systems in high-stakes domains need a similar redesign. A single recommendation is often the most dangerous output format. Tactical environments like logistics, finance, emergency response, infrastructure operations and security need branch structure. They need contingencies, probabilities, costs, and abort thresholds. If a system cannot show alternatives and explain why a branch was taken, you cannot audit it. If it cannot state when to stop, you cannot govern it. Confidence displays become actively harmful when they are detached from calibration and institutional authority. Autonomy in the physical world pushes the accountability question even harder. Consider vessel-class autonomy, meaning an autonomous AI bound to a specific vehicle or installation. The key issues arrive long before anyone debates sentient ships. Liability, jurisdiction, insurance, command authority, telemetry, and incident reconstruction become immediate. A machine that can act in physical space must have an operating envelope, a clear chain of command, and a recorder that supports after-action reconstruction. Without those, you get an autonomy attribution crisis, where nobody can prove who authorized what. Distance makes that harder. Distributed intelligence under light-speed delay forces a design choice. Either local nodes have delegated authority, or they fail while waiting for instructions that cannot arrive in time. That reality shows up in off-world infrastructure, underwater systems, remote industrial sites, and any environment with unreliable communications. In such settings, cryptographic command, delayed verification, conflict resolution procedures, and strict trust boundaries are not optional. They are how you prevent local autonomy from drifting into local divergence. All of this sits on top of a deeper, long-arc constraint. Computation is not limited by a single bottleneck. There are engineering limits like memory bandwidth, interconnect, reliability, and tool safety. There are coordination ceilings like delegation, auditability, institutional trust, liability, and misuse control. Then there are hard physical limits like thermodynamics, quantum noise, speed of light delay, and finite information capacity of substrates. The frontier moves by working across all three, not by winning any one race. That is why the long-term story is substrate diversification, not a single replacement technology. Quantum computing may matter, but only where error correction, workload fit, and verification make it useful. Quantum sensing and communication are separate categories, and may become infrastructure relevant sooner. Photonics and optical compute target bandwidth, heat, and interconnect limits, but must be judged on integration and precision, not hype. Neuromorphic systems are best treated as efficiency and architecture options, especially for always-on sensing, edge autonomy, and adaptive control, where joules per inference dominate. Biological and molecular computing likely trade speed for density and chemical specificity, first affecting storage, diagnostics, and embedded control. Even slow substrates can be valuable when durability and low maintenance matter more than fast cycles. One idea ties these threads together. Computation should be treated as civilizational architecture, not a product category. Faster and cheaper reasoning does not automatically produce legitimate decisions. Simulation is not governance unless authority, consent, and accountability are specified. Digital twins are not truth unless calibration, provenance, and uncertainty are maintained. An agency is not productivity unless permissions and rollback are real. So the practical implication is simple and difficult. Build the control planes, cost ledgers, and audit trails first, because capability without governance is just speed without steering.